Section 10.5, Conic sections. Parabolas, ellipses, and hyperbolas are called conic sections or conics because they result from intersecting a cone with a plane as shown. So we take a double cone, we consider it completely hollow, so we're only considering the shell of the cone, the candy coating, and we slice it. Either we get an ellipse, either we get a parabola, or we get a hyperbola if we slice all the way from top to bottom. So if we slice with the ellipse fashion in a perfectly straight way, then we actually get a circle, which is a special case of an ellipse. Let's consider parabolas first. So parabolas are sets of points in a plane that are equidistant from a fixed point f, called the focus, and a fixed line, called the directrix. This definition is illustrated over here, and notice that the point halfway between the focus and the directrix lies in the parabola. Over here. So halfway between the focus and directrix, it is called the vertex. The line through the focus perpendicular to the directrix is called the axis of the parabola. So we have an equation of the parabola with focus 0p and directrix y equals negative p. So that means that we're considering our axis of the parabola to be the y-axis. So this is a y equals parabola we just solved for x squared. Let's see if we can come up with this equation though, using the definition that says that this distance is equal to this distance for any point on a parabola. So if those two distances are equal, let's look at the distance from the focus to a point. So first, let's call this point something. How about xy? And we'll put our parabola on the x-axis. So the axis of the parabola is the y-axis. And let's say that this point over here, this focus, is at 0p. Then this distance from 0p to xy is just by the distance formula the square root of x minus 0 squared, which is x squared, plus y minus p squared. That's the distance from 0p to xy. So that has to be equal to this distance, which is the distance from the point to the directrix. So let's figure out what that distance is. Well, this distance over here is just the y value. And then our focus is at 0p. So that means that from here to here is p. So from here to here is p. So this is p. Because remember that the vertex is halfway between the focus and the directrix, so it's symmetrical p on top and bottom. So this means that the distance, our first distance from the focus to the point, must be equal to distance from directrix to the point, so that's the absolute value of y plus p. So we can just square both sides. We get x squared plus y minus p squared is equal to y plus p squared. And we can multiply out. We get that x squared plus y squared minus 2py plus p squared must be equal to y squared plus 2py plus p squared. We just foiled the left and foiled the right. We'll really foil this part. X squared is just x squared. So then notice that we have a y squared on both sides, so that cancels. We have a p squared on both sides, so that cancels. We just add the negative 2py to both sides, and we get x squared equals 4py. And then we can do a quick substitution if we have a x equals parabola to get y squared equals 4px. So in this case, the focus is on the x-axis instead of the y-axis. So how about we find the focus and directrix of the parabola y squared plus 10x equals 0 and sketch it. So let's put this in the form that we had before, which was y squared equals 4px. So y squared equals minus 10x by subtracting 10x from both sides. And if that's supposed to equal 4px, then that means that 4p must equal negative 10. So that means that p must equal negative 5 over 2. So our focus is at negative 5 over 2, 0. And our directrix is at 5 over 2. So if we're going to draw this, let's see. I'll put in some lines and make this the y-axis. This can be the x-axis. That's 0. How about I do my focus and directrix first? So here's my directrix. This is x equals 5 over 2. And I'll put my focus equidistant. So here's my focus at negative 5 over 2, 0. And now all I have to do is sketch my parabola. So my vertex is in between my focus and directrix, so that's over here. And I should end up with a parabola something like this. So this is the parabola y squared plus 10x equals 0. An ellipse is the set of points in a plane that the sum of whose distances from two fixed points, f1 and f2, is a constant. These two fixed points are called the foci, or foci, which is the plural of focus. So if we have minus c0 and c0 as the foci of an ellipse, then the sum of the distances from a point on the ellipse to the foci are 2a, and b squared equals a squared minus c squared. So then over here, this would be, well, all the way, would be 2a. The points a0 and minus a0 are called the vertices. So here's minus a0, here's a0. The line segment joining the vertices is called the major axis. So this blue line I just drew is the major axis, and the line segment joining 0b and 0 minus b is the minor axis. So this would be the minor axis in this case. Let's see if we can come up with an equation for our ellipse that's similarly that we came up with the equation for our parabola. So we're going to say that it becomes x squared over a squared plus y squared over b squared equals 1. So if the foci are at plus or minus c0, and our definition is that the sum of the distances from an arbitrary point to the foci is equal to the length of the major axis, then how about we draw the x-axis, because we're putting this thing at the origin, and we will put it in an arbitrary point. Do it like that. So this point P we'll call xy. So we want to show that if we take these two orange pieces and we add them together, that we get this major axis over here. So, well, we don't actually need to show that. That's by definition. We're going to use that. So we'll put our first focus, f1, at minus c0, and our second focus, f2, at c0. So then we want the distance from f1 to p. So that's, by the distance formula, the square root of x plus c squared, because it's x minus minus c, and plus y minus 0 squared, so that's just y squared. Then we'll add that to our other distance for f2 to p. So that's x minus c squared plus y squared. And that should equal this distance from here to here, the major axis, which is 2 times a, because our vertices are at a0 and minus a0. So what we can do is we can subtract this square root from both sides. So we get that the square root of x plus c squared plus y squared is equal to 2a minus the square root of x minus c squared plus y squared. So what we can do now is square both sides. And when you do that, you get a complete mess. However, it does simplify out. When you end up squaring everything through and then you cancel out a whole bunch of terms, you should end up with a times the square root of x plus c squared plus y squared is equal to a squared plus c times x. And if you don't believe me, try multiplying the right side out, because when you square this, you have to FOIL. Squaring this is easy, but the other side is what becomes painful here. So we get this. What we can do is square it again. And squaring it the second time isn't as bad as the first time, although it's still not that pleasant. You get a squared times x squared plus 2cx plus c squared plus y squared is equal to a to the fourth plus 2a squared cx plus c squared x squared. And what you can do is distribute your a squared and then group together all of your squared terms. Factor out the square and you get a squared minus c squared times x squared. And then you get plus a y squared. So all of that equals a squared times a squared minus c squared. So notice we have no b at this point. We introduce b as the value of a squared minus c squared just to simplify our notation a little bit. So we let b equal to a squared minus c squared, so we get bx squared. Sorry, we get b squared equals a squared minus c squared, so b squared x squared plus a squared y squared. Oh, this should have been a square over here. A squared y squared equals a squared b squared. And then we divide everything by a squared b squared. We end up with x squared over b squared plus, x squared over a squared plus y squared over b squared equals 1, which is what we wanted. So in order to do this, we had to define b to be a squared minus c squared, which is where we got this equation from, where c squared is a squared minus b squared. We had to define that these distances were equal to each other. This plus this equals our major axis. And then we just had to do some nasty algebra. If we do a quick substitution, then we get the ellipse that has a major axis that's vertical instead. So it looks like that instead of our horizontal ellipse that we did. Let's sketch the graph of 9x squared plus 16y squared equals 144 and locate the foci. So let's divide everything by 144 so that it equals 1, like in our standard equation. So we have x squared over 16. When we divide by 144, 9 over 144 is 1 over 16. And we have y squared over 9 equals 1. So this means that it's x squared over a squared, so a is 4. And b must be 3 then. So c squared is equal to a squared minus b squared. So that must be 7, 16 minus 9. So that means that c must be the square root of 7. So let's draw this now. So how about we put in our a is 4, so this would be 4, 0. And then we'll put minus 4, 0 over here. And since we know that b is 3, that means that our minor axis goes from 0, 3 to 0, minus 3. So we can connect this and we'll get hopefully something that almost resembles an ellipse. Yeah, I'll connect the other way. Okay, roughly ellipse, yeah. So let's do our foci now. We've got one at rad 7, 0, so it's like somewhere over here. And we've got another one at minus rad 7, 0. So that's our ellipse. Let's now find an equation of the ellipse with foci 0 plus or minus 2 and vertices 0 plus or minus 3. So this time we don't have the equation, we need to find it. So since the foci are at plus or minus 2, that means that c must equal 2. And since the vertices are at 0 plus or minus 3, we have a equal to 3. So let's find b. We've got b squared equals a squared minus c squared. So that's going to be 9 minus 4, which is 5. So that means that we have, well, we have to be a little bit careful here. In this case, the vertices are 0 plus or minus 3. So when x equals 0, they're on the y-axis. So in this case, a is underneath y. So we have x squared over b squared, which is x squared over 5. And we have y squared over a squared, which is 9. And that equals 1. So that's the equation of our ellipse. If we want, we can multiply by the common denominator of 45 on the left and right, and we can get 9x squared plus 5y squared equals 45. In any case, we've got an equation of our ellipse. Let's talk about hyperbolas now. A hyperbola is the set of all points in a plane, the difference of whose distances from two fixed points, and the foci, two fixed points f1 and f2 called the foci, is a constant. This definition is illustrated in this figure. So instead of taking these orange pieces and adding them together, we take this orange piece, we subtract the other orange piece, and that has to equal the distance between the vertices. So let's take a look at the equation. Instead of x squared over a squared plus y squared over b squared, we just end up with x squared over a squared minus y squared over b squared. That's assuming that our ellipse looks like this where it's horizontal. Our hyperbola looks like this where it's horizontal. If it's a vertical hyperbola that looks like this, then we get y squared first and subtract the x squared term. You can prove this pretty much the same way that we proved, well, I don't know about proof, you can derive this the same way we derive the equation for an ellipse by calculating this distance, and calculating the distance between them, and then just subtracting instead of adding. Because all we did before was add and saw that it was equal to 2a. In this case, we just have to subtract, and then we'll pretty much derive it the exact same way. So I won't do it again. Instead, let's jump straight to an example. How about we try to find the foci asymptotes of the hyperbola 9x squared minus 16y squared equals 144 and sketch its graph. So notice there's one extra thing that hyperbolas come equipped with that ellipses don't, and that's these asymptotes, which are at plus or minus b over a times x. So that means that if we draw a line over here, it's an asymptote, and we draw a line over here, it's an asymptote, and the slope of the asymptote is either b over a or minus b over a. So let's see, we've got 9x squared minus 16y squared equals 144. Let's divide by 144. So we get x squared over 16 minus y squared over 9 equals 1. So that means that a must be 4 and b must be 3. Notice for hyperbolas, a is always underneath the first term. So we have c squared. It's not a squared minus b squared. For hyperbolas, it's the opposite. So it's 16 plus 9, a squared plus b squared. So c squared is 25. So I think we have enough information. We can graph this now. Put in some axes. And how about we do our asymptotes first? So we have an asymptote at plus or minus a over b times x. So, sorry, plus or minus b over a. A over b is for the y first hyperbolas. We have x first. So it'll be plus or minus b over a times x. So that's our slope. So that means that it's slope of 3/4. So it should look roughly like this for our asymptote. And we'll call that line y equals 3/4 x. And then we'll do the same thing for minus 3/4 x. So now I think we'll put in our foci, might as well at this point. So we've got 1 at 5, 0, because c squared is 25. So we could put that in somewhere around there. And we've got another 1 at minus 5, 0. So now let's actually draw our ellipse. We have a vertex at 4, 0. And we have another vertex at minus 4, 0. Because a is 4. So we just draw near our asymptotes and we get a rough ellipse, basically 2 parabolas. I think I said ellipse, but I actually meant hyperbola. Hyperbola, hyperbola, hyperbola. Let's find the foci equation of the hyperbola with vertices 0 plus or minus 1 and asymptote y equals 2x. So if the vertices are at 1, that means that a is 1. And, in this case, x is 0, so they're on the y-axis. So that means that our asymptotes are a over b times x. So we're looking at a over b equal to 2. Because the asymptote was y equals 2x. So if a over b is 2, that means that b, which is equal to a divided by 2, is equal to 1/2. So c squared is equal to a squared plus b squared must be 5 over 4. So our foci are 0 plus or minus the square root of 5 over 2. And our equation is y squared over a squared, which is 1, minus x squared over b squared. So that's x squared over 1/4. Dividing by 1/4 is the same as multiplying by 4. So that's our equation of our hyperbola. Let's now find an equation of an ellipse with foci 2 minus 2, 4 minus 2, and vertices 1 minus 2, 5 minus 2. So there's no zeros anywhere. So in this case, our ellipse must be floating somewhere else other than the origin, so we have to be careful to translate our x and y coordinates. Well, in order to try to find out what our a and b are, we need to look at the complete distance between our foci and our vertices. So 2a is how long our major axis is. That's the distance between our vertices. Notice we have vertices at 1 minus 2 and 5 minus 2. So they're both just along the line y equals minus 2. So all I have to do is look at the difference between the x values for the distance between them. So they go from 1 to 5. So that means that 2a is equal to 5 minus 1, because it's the distance between. So that must be 4. So the length of the major axis is 4. That means that A must be 2. Similarly, we look at the difference between the foci to figure out what C is equal to. They're both still, of course, along the line y equals minus 2 because they're in line with the vertices. So we look between 2 and 4, we subtract, we see that 2C is equal to 4 minus 2, which is 2. So that means that C is equal to 1. Then B squared is equal to A squared minus C squared for ellipses. So that must be 3. And therefore, we're dividing by 4 for x. See, notice that our vertices are along a line y equals minus 2. So that's parallel to the x-axis. So that means it's x that divides a. X gets the bigger number underneath because it gets stretched more. So we'll divide something with x by 4, and we'll add that to a y term divided by 3. That'll equal 1. However, we can't just put x squared over here and y squared over here because, in this case, our center of our ellipse is not at the origin anymore. We have to translate our x and y coordinates. So let's see how much they had to translate by. Well, our vertex must be halfway, well, not our vertex, our center must be halfway between our vertices. So our vertices were at 1 minus 2 and 5 minus 2. So halfway between them is the midpoint. 5 plus 1 divided by 2, that's 6 divided by 2, which is 3. So the center of our ellipse must be at 3 minus 2. So that means I can take x and translate it by 3, so I subtract 3. And I take y and translate it by minus 2, so that's plus 2, because minus minus is a plus. Okay, let's take a look at this conic. 9x squared minus 4y squared minus 72x plus 8y plus 176 equals 0. We don't even know if it's a parabola, hyperbola, or ellipse yet. So how about we try to complete the square? In order to do that, I want to try to make everything just equal some constant. That way we can divide later and have everything just equal 1. So how about we move everything that's not 176 over to the other side? So we'll end up with 4 times y squared minus 2y minus 9 times x squared minus 8x equals 176. I took all of this stuff, I moved it over to the other side, and then I just factored out 4 and a 9 so that I could get x squared and y squared by themselves. Now I can complete the square. So I complete the y squared by just adding a 1 inside. So adding a 1 inside completes that square. So that means that I need to add 4 to both sides because it's being multiplied by 4. I can't just add 4 to one side of the equation, not the other. So I'll keep that in mind. I do the same thing for the x squared that I want to complete the square on. Half the middle term of 8 squared is 16. So that's what I have to add to complete this square. So I get 176 plus 4 because I added 4 over here. And I have to add, well, in this case, I subtracted 9 times 16 on this side. So I have to subtract 144 from the other side to balance it out. So I end up with 4 times y minus 1 squared. That was the whole point of completing that square. Minus 9 times x minus 4 squared equals 36. Because that's what this simplifies to. So then I just divide by 36. And I get y minus 1 squared over 9 minus x minus 4 squared over 4 is equal to 1. So because y is first, that means that my asymptotes are a over b. So they'll be at 3 over 2 for the slope. So how about we can do that first. So I'll put in my y-axis. I'm translating this over x by 4 and y by 1, so I'm going to lean towards the first and fourth quadrants. So let's do our asymptote. We can also do our center. Notice our center is x equals 4, y equals 1. So I'll put that in. So that's the center of hyperbola at 4, 1. And let's do our asymptotes. Asymptotes at a over b times x, and they just get translated by 4 and 1. So there's one asymptote. And that'll be the asymptote y minus 1, because y had to translate by 1. And our slope is a over b, so that's 3 over 2 times x minus 4. We just had to remember that our slope is still 3 over 2, but our y and x values were translated because everything is moved around. We do the same thing to get our other asymptote. Alright, so that's going to be y minus 1 equals negative 3 over 2 times x minus 4. And now we can put in our vertices. So it looks like a is equal to 3, because a squared is 9. So that means we go from our center up 3. So we should go to 4, 4. And we should go from our center down 3 to 4 minus 2 for our other vertex. And then we just draw so that they approach the asymptotes. Yeah, that's our hyperbola.